So we know how to find the area between two curves in rectangular space, and we know how to find the area between a curve and the pole in polar space. So we can put those together and find the area between two polar curves, right? So we have an inner curve right here, right? So that's the inner curve. Oop, I better change my color there. Right, so inner. And then we have an outer curve out on the outside right here. And so the area between them is this region right here, right? And so I want to find that area. Well, what you would do is you would find the area of from the pole out to the yellow curve, which is the outer portion, and then you would subtract the area in here, right? So you take the outer minus the inner. So let me draw another picture really quickly. So what you're sort of doing is you take the whole section, that's the outer piece, and then you have this inner piece in here. And if you subtract away that inner piece from the outer piece, you'll have what's left over, right? So you're taking the whole bit minus the little bit inside, and that'll leave you this region left over. And that is how to find the area of a region. Of course, to find those sectors in the first place, it's 1/2 r squared, right? So 1/2 r squared d theta is if it's just a regular curve. So when we have a subtraction, we subtract the two, but they're still 1/2 r squareds. So you have your outer and then your inner. All right, so it seems pretty straightforward. And it is, except for which curve is the outer curve and which curve is the inner curve has to be determined. And of course, they could cross over. All right, so let's start with an example. We want to find the area of the region inside the curve r equals the square root of cosine of theta, but outside the circle r equals 1 over the square root of 2. Now, I graphed these in Desmos, so we can double check them, but I think we all know which one's which, but just so we're clear. All right, so the one that is r equals the square root of cosine is the kind of jelly bean shaped one. So it's I believe a limaçon. And then in the blue one for me is a circle. Okay, so I want to be inside, let's read this again, inside the region, inside this curve. So I want to be inside here, but outside of that circle, which means I'm talking about this kind of half moon. That's what I'm trying to find. That is inside the red curve, but outside of the blue curve. So we're noticing that this red curve I have is my outer curve. So that's f of theta, which is the square root of cosine theta, is the outer curve, right? Because it's definitely on the outside here. The inner curve is right here. So that'd be g of theta, which is 1 over the square root of 2, which is the inner curve. Wonderful. So that helps because then when I want that area, it's 1/2 the integral from alpha to beta of f of theta squared minus g of theta. It's a theta squared d theta. All right, so I've already figured out that f of theta goes here, g of theta goes there. Lovely. All right, so this is 1/2. I know that I'm going to put in the square root of cosine theta squared minus 1 over the square root of 2 squared d theta. Wonderful. Okay, so now I just have to figure out what I'm going to do about my limits of integration. So I need to be able to figure those out. So I'm going to go to the side and figure those out, kind of down here actually. So I need to find the intersections, because if I'm going to find the limits of integration, I need to know where these two graphs intersect. Find intersections. Well, you're really finding theta at the intersections. That's what you're looking for. Because you need those theta values, because theta is what you're integrating with respect to. Okay, so if they're going to intersect, that means that f of theta is going to be equal to g of theta. All right, well, that means that the square root of cosine of theta will be equal to 1 over the square root of 2. Well, obviously, I'm going to square both sides. I mean, who wants to deal with the square root? So that would mean that the cosine of theta, squaring it, is equal to a half. Okay, well, I know my unit circle. Cosine of theta is equal to a half, right? At, well, it's the x value, so it's going to happen right here, right? And then right here, right? So it happens at pi over 3. It happens at 5 pi over 3, which is technically negative pi over 3, right? And then so on. Okay, so theta is equal to pi over 3, 5 pi over 3, or negative pi over 3. There are more, but we're just going to stop right there. Now, I'm not going to use pi over 3 and 5 pi over 3. Pi over 3 to 5 pi over 3. So pi over 3 is obviously here. So if I drew this line right here, you can kind of see, like, that's pi over 3. So that makes sense, right? We just found that, so that's true. If I go pi over 3 to 5 pi over 3, that would be finding from here all the way around. It would be finding this, like, Pac-Man kind of zone. And that's not what we want, right? Oop, I was a little off the line there, right? So that's not going to work. So I don't want to go pi over 3 to 5 pi over 3. That won't work. But what I do want to do is go from negative pi over 3 up to pi over 3. So this one's out, right? Because that one would make it so that if I drew the picture, right, here's the picture like this, it'd be finding this zone, which isn't what we're interested in, right? That's no good to us. So it's these two that we care about. So we're going to go from negative pi over 3 to pi over 3, because negative pi over 3 is down here, and pi over 3 is up here. And I'm going to kind of separate this. All of that is kind of work that you do on the side. You have to go figure out your limits of integration. You have to find your intersections, because those will give you those limits of integration, and kind of throw out ones you don't need, etc. And remember that you're sweeping through an arc. So this makes sense. I want to go from negative pi over 3, chug, 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 through to pi over 3, right? That's how they work, because it's always sectors, pieces of pie, pieces of pizza coming out from the pole, right? So pi over 3 to 5 pi over 3 would not work, but negative pi over 3 to pi over 3 works. But let's be smart about this. I mean, pi over 3 and negative pi over 3 is fine, but it's kind of more of a pain to deal with than we really need. So let's be brave, and let's think to ourselves, this is symmetric. What if I just find that portion? I could do that, right? How would I do that? Well, I would take it and say, hey, this is true, but why don't I do 2 times a half integral from 0 to pi over 3. Because that's 0, the positive polar axis right here. Oop, that's a 0. It looks like a theta now. Hold on, I'm gonna change it. My paper moved on me. All right, so I'm gonna go 0 to pi over 3, but then I'll multiply it by 2, right? So I'm taking the area I want, I'm cutting it in half, so then I have to multiply by 2 to make this work. And then I can square this right now and get this over with. This will be square root of cosine of theta squared is cosine of theta minus 1 over the square root of 2 squared is 1/2. And I want to integrate that with respect to theta. 0 will be a lot easier to work with when the negative pi over 3 was going to be. All right, see why we do it? All right, so 2 times a half gone, so don't have to worry about that. The integral of cosine is negative sine of theta minus 1/2 theta. And I'm going to take this from 0 to pi over 3. Actually, I'm going to keep my color coding just for those pieces to make it clear. Okay, so when I put pi over 3 in, that would be the negative sine of pi over 3 minus 1/2 times pi over 3. And all of that is minus the negative sine of 0 minus 1/2 times 0. And if you're thinking what I'm thinking, you're thinking that's all 0, and the answer is yes, it is. That's why we did 0, because 0 is easier. Okay, so this whole thing is 0. Don't have to worry about it. Done with that. The sine of pi over 3. Pi over 3 is this angle, so its sine is the square root of 3 over 2. So this is negative square root of 3 over 2 minus, and that would be pi over 6. That is the actual answer right there, right? So, oh, whoops. I'm losing my brain. The integral of cosine is positive sine, not negative sine. The derivative of cosine is negative sine. Sorry, I messed that up. It's positive, sorry. The integral of cosine is sine. So that's sine, and that's positive the square root of 3, and then technically this is positive sine right here, but it doesn't make any difference because that was 0 anyway. Sorry about that. Integral of cosine is sine because the derivative of sine is cosine. So this is the answer. It's square root of 3 over 2 minus pi over 6 feet squared. If you want that in decimal form, of course, we can go into Desmos and do that. So I could take the square root of 3, divided by 2, and minus pi divided by 6. Now, if I want to verify that that is, in fact, the integral that I wrote in the first place, I could take the area integral that I originally wrote. So 1/2, we went from negative pi divided by 3 to positive pi divided by 3. And it was of, lots of parentheses in here, square root of cosine, I'll do x, cosine of x squared minus 1 over the square root of 2 squared dx. Sure enough, they're the same. So it does work out and verify in Desmos if I want it to. Oops, I forgot already. What was the decimal? 0.3424.